Now we'll add the main script file for problem 0001. Let's open the file and start coding step by step. Let's start by importing the list type for hints, and note the brute force approach and its complexities. This import enables clean type hints for lists throughout our methods. Now we'll define a solution class and a brute force twosome method that tries every pair using nested loops. The inner loop only checks indices after I to avoid duplicate pairs and self-pairing. Here we check if the current pair sums to the target and return the two indices immediately when it does. This condition is equivalent to nums I plus nums j equals target. Next, let's document a more efficient hash map approach and its complexity. We'll reduce the time from quadratic to linear by trading a little extra memory. We redefine solution to present an alternative implementation and initialize a map to remember scene values and their indices. Number map will map each number to its index for O1 lookups. We iterate once, compute the complement we need, and if we have already seen it, we return the matching indices. Checking the complement in the map turns the search into constant time for each element. Otherwise, we store the current number's index for future matches. If no pair exists, we return an empty list. Storing after the check prevents using the same element twice for a pair. Finally, let's outline a two-pointer variant and its complexity notes. This strategy assumes the list is sorted and typically returns value pairs rather than indices. We redefine solution once more to show the two-pointer flavor, initialize result storage, and set pointers at both ends. The left and right pointers will converge towards the middle to find valid pairs. While left is before right, we compute the current sum. If it's too small, or we'd repeat the same left value, move left forward. This loop keeps scanning until the two pointers meet. If the sum is too large, or we duplicate the right value, move right backward. Otherwise, we found a valid pair to record. Shrinking from the right helps reduce the sum and avoid duplicate pairs. After adding a pair, we advance both pointers to continue searching and finally return all found pairs. This returns a list of value pairs that meet the target using the two-pointer approach. Now let's add a quick test. Because the latest class definition overrides earlier ones, this call uses the two-pointer version. With a sorted input, the two-pointer version will print the value pair for the target. Earlier implementations show brute force and hash map indices. Now we'll add the Python file for problem 0002, add two numbers. Opening the solution file so we can start coding step by step. Let's start by noting the time and space complexities and importing optional for type hints. We use optional because our list nodes can be none at the ends. The comments summarize the algorithm's efficiency. Before the solution class, we'll recreate LeetCode's list node so we can run local tests. Each node stores a value and a reference to the next node. This mirrors LeetCode's node structure, letting us build and traverse linked lists in our examples. We add a readable representation, so printing a node shows the chain, which is useful for quick debugging. This helper makes the output human-friendly by showing the path through next pointers. Now we'll add the solution class, which is the expected container for LeetCode methods. Placing the logic inside solution matches the LeetCode interface. Let's define add two numbers, which takes two reversed linked lists and returns the head of their sum as a new list. The type hints show nodes can be none, and the method returns a linked list head for the sum. Now we'll add a dummy node to simplify list construction and a cur pointer to build the result, along with a carry for digit overflow. Using a dummy, Sentinel avoids special casing the head. Cur will always point to the tail we're extending. Next, we iterate while there are digits left in either list or a remaining carry. We read each digit, treating missing nodes as zeros. This condition cleanly handles different list lengths and any final carry after the last nodes. We sum the two digits with the carry, use divmod to split the new carry and the current digit, and append a node with that digit. Divmod neatly returns the tens place as carry and the ones place as the node's value. Now we'll advance the tail pointer and move forward in L1 and L2 when possible to continue the addition. Advancing pointers keeps the loop progressing through both lists safely, even if one ends earlier. Finally, we return the real head of the new list, which is the node after the dummy. Returning dummy.next cleanly hands back the constructed list without the placeholder node. Let's add a quick smoke test. 0 plus 0 should produce a single node with value 0. You can replace L1 and L2 with longer lists to experiment, like 2-4-3 plus 5-6-4 to get 7-0-8. Now we'll add the solution file, where we'll build the sliding window approach step by step. Opening the file so we can begin coding the solution. Let's start by documenting the time and space complexity and importing counter to track character frequencies efficiently. Counter gives us constant time increments and decrements as we slide the window. Next, we'll define the solution class, which is the interface LeetCode expects. LeetCode will instantiate this class and call our method on the input. Now we'll add the method signature, which accepts the string s and returns the length of the longest substring without repeats. We'll implement the classic sliding window pattern inside this method. We'll use a counter to track counts in the window, 2 pointers left and right to define the window, and residential to remember the best length scene. Chars keeps the frequency of characters currently inside our window so we can detect duplicates. We'll expand the window by moving right, read the new character R, and increment its count in chars. Each index is visited at most once by write, keeping our runtime linear. If adding or creates a duplicate, we shrink from the left, read L at left, and decrement its count. This inner loop restores the invariant. The window contains only unique characters. We advance left until the duplicate is removed, update the best window size, and then move right forward to continue exploring. Window size is computed after duplicates are resolved, ensuring it's a valid substring with unique characters. Finally, return the maximum length found across all valid windows. This completes our sliding window implementation. Let's add a quick test using the sample input to verify the result. We expect 3, since ABC is the longest substring without repeating characters in the sample. Now we'll add a new Python file where we'll implement and teach two approaches, a logarithmic time cut method and a linear time merge method. Let's open the file and start writing our solution step by step. Let's start by documenting the complexity of our first approach and importing lists for type hints. The typing import helps us communicate expected input and output types clearly. Now we'll define our solution class and method. We compute the lengths of both arrays and their total size. These variables let us reason about positions across both arrays when searching for the median index. Next, we define a helper that finds the kth element via binary elimination on index ranges. If one array segment is exhausted, we pick directly from the other. When the current window in nums1 is empty, the kth element must lie in nums2 at the corresponding offset. We compare midpoints. If the combined mids are before our target, we discard the lower half of one array based on which midpoint is smaller. Taking mid-indices in both ranges lets us drop about half of the search space each step. If nums1's midpoint is smaller, we skip its left portion. Otherwise, we skip nums2's left. If we're not before the target, we drop the opposite halves. Here we trim the upper part of nums1's window, narrowing the search when mids are already at or beyond the target. When mids are not before the target, we prune the right side accordingly. Finally, we call binary cut for the middle index, or take the average of the two middle elements for even total length. For even total length, we average the two central kth elements to get the median. Now we'll add a straightforward O-in merge-based approach, redefining solution to provide an alternative implementation. This second solution class will be the one used by our test code below. We'll track two pointers and define a helper that returns the next smallest element while merging both arrays on the fly. Using non-local lets the helper update our outer pointers as it consumes elements. If nums1 has the smaller front element, we take it and advance idx1. Otherwise, we take from nums2. Advancing the pointer moves our merge forward one step. We also handle boundary cases. If nums2 is exhausted, we must take from nums1, otherwise we'll fall back to nums2. When nums2 is fully consumed, all remaining elements must come from nums1 in order. If nums1 is exhausted, we take from nums2. The helper returns the chosen element. Then we compute the total length to locate the median position. Each call to getMin returns the next element in the merged order, just like one step of merge sort. We compute the halfway index. For even totals, we advance mid one steps, so the next two elements are the two middle values. Even length arrays require averaging the two central elements. We grab the two middle elements and average them. Otherwise, for odd totals, we consume mid elements to land right before the median. This returns the correct median when the merged length is even. Finally, for an odd total length, the next element we pop is exactly the median. We return the middle element directly for odd-sized merged arrays. Now let's add two quick tests, one odd total case and one even total case, to verify both scenarios. These calls exercise our final solution class, which uses the linear merge approach above. Now let's create the Python file, where we'll build the solution step by step. Opening the file so we can start coding. Let's start by stating the optimal approach and its complexities. We'll implement Manager's algorithm for linear time palindromic substring search. Manager's algorithm expands around centers while reusing previously computed radius information to stay linear. Now we'll define the solution class and the method signature we need for LeetCode. A short docstring explains the approach. This method takes the input string and returns the longest palindromic substring. We pre-process by inserting separators to unify even and odd palindromes. Then we prepare an array to store radii and track the current center and rightmost boundary. The separator trick lets every palindrome be treated as odd length, simplifying comparisons. Now we iterate each position as a center. We compute its mirror with respect to the current center and seed the radius if we're inside the known right boundary. The mirror index reuses symmetry, so we don't re-expand characters we've already confirmed. We expand around I as long as characters match. If we reach further right than before, we update the center and right boundary. Updating the center and right boundary is the key optimization that keeps the algorithm linear. After the loop, we translate from the transformed string back to the original indices and return the longest palindrome substring. The start index divides out the separators to map correctly into the original string. For comparison, let's include the brute force approach and its complexity. We'll scan all substrings and check palindromicity. This baseline is simple but far too slow for large strings, which motivates the optimized methods. We define a helper to verify if S, I, J is a palindrome by 2 pointers moving inward. This check runs in O length for each candidate's substring. We try lengths from largest to smallest to return early. If any substring is a palindrome, we return it immediately. Iterating lengths, descending ensures the first match is the longest. If nothing is found, return empty string. Now let's add a dynamic programming approach with quadratic time and space. DP uses a table where DP L R is true if SL R plus 1 is a palindrome, building from shorter to longer substrings. We initialize the DP table and handle an empty string edge case. This n by n table tracks palindrome truth values for all substrings. Every single character is a palindrome of length 1. We'll expand window ends with right and left pointers. This seeds the diagonal of the DP table since each single char is a palindrome. A substring is a palindrome if its ends match and the middle is a palindrome, or it's short enough to be trivially true. Track the longest seen so far. Once DP, left, right, is true, we may update our best length and answer. Finally, we return the longest palindrome and add 2 sample test cases to verify the implementation. These quick checks should print palindromes like BAB or ABA for the first input and BB for the second. Now we'll add our solution file named 0006-zigzag-conversion